This is going to be my lab 5 for Physics 2011. My name is Rafi Hadi. Let's get started. So I'm going to be covering the motion of a falling slinky option, right? What we're going to do is we're going to use Tracker to track the motion that we see in the video of the falling slinky, and I'll show that later on. I'm going to have a simulated model at the same time, coded in GlowScript, and I'm just going to compare the real-life result that we get to the simulation, right? So that's just a basic introduction. So the result that we get is, as you'd expect, right? The bottom of the slinky stays in place as tension and gravitational forces balance out, and it remains motionless until the top of the slinky descends and reaches the bottom, which causes the entire slinky to then fall, right? And that's, if you watch the video, that's exactly what happens there as well, right? So what physics principles are in use here? Newton's second law for one, right, which we've seen in pretty much every lab. And that's just that the final velocity is equal to F net divided by mass times the change in time, right? So velocity final equals the net force divided by the change in time multiplied by the mass, right? Straightforward enough. And then, of course, we use the position update formula, which I have here, and the velocity update formula I have here as well. And then generally, we have the principle of drag, right? That's acting in the opposite direction of the motion of the slinky. And I have that more on the next page here, right? So we have Ft, this is the drag force, right? Ft equals minus b, absolute value of v squared times v hat. That's the value of drag. And we also have gravitational force acting here, right? So that's just 0 minus mg0 with the gravitational constant of 9.8 meters per second squared being multiplied here as g. And then drag force, as I already mentioned, that's the force that's opposing the movement of the object. So these are all the different forces that we account for in our GlowScript motion and what caused the slinky to move the way that it does. So what two different models do we have? In our experimental model, we're just measuring the position of the slinky and the corresponding time data via tracker, right? So we're analyzing the relationship between the position and the time of the slinky. In our computational model, which was developed via GlowScript, we're using the anticipated position of the slinky against time, and this is estimated by our computational model, and I'll show that more later on. First of all, for tracker, right, just use normal the manual tracking that you have in tracker, where you click frame by frame to get a sense of the movement of the object. And this is sort of generally the graph that I got that you can see here on the right. This is a result that we got from using tracker. And now for our GlowScript code, right? It's pretty straightforward. These are the initial conditions that I set. These are roughly pretty accurate based on the way that the video was calibrated in tracker, right? This is just the estimated mass of the ball. And this is the delta t is the time step that we're using for our graph, and this is just some basic values. This is the unit vector direction in which everything's happening, right? It's the positive y-axis. This is the magnitude of gravity, etc. Now here, right, we're just doing some very basic formulas that we already discussed in our in the physics principles section of this lab, right? You can see here we're just applying Newton's second law in order to keep updating our velocity, F net divided by mass times delta t. You can see that happening right there. And we're just updating the position using the position update formula with that as well. And we keep advancing the clock with each iteration, right? So that's essentially how we're predicting the motion. We're just using these very basic principles of physics in order to keep predicting and updating our motion, right? Yeah, and you can see here this is where we're calculating stuff like net force and drag, net force, drag, etc. So Fd here, this is drag, and generally this is W, this is just our weight, and F net is just weight minus drag, right? So that's how we're doing that. And again, we're applying the momentum principle to make sure that everything's fine, just based on, again, the old physics principles that we had that we've already talked about regarding this lab. That we keep advancing the clock based on that, right? So just to recap, right, before roughly the 5.4 second mark, we're just doing this very basic formula here. We don't have drag involved at all. But once it starts falling, right, so between that 5.4 second point and this point, right, you can see here now we have drag involved as well. Basically, that's the big difference between this and this. If you look, right. So that's basically how our GlowScript model works, right? And you can see that up until roughly the 2-second mark, the things are pretty straightforward. And then this is the graph that we get for position against time. And if we compare our tracker result to our GlowScript result, right, we can see that they're pretty similar, but the predicted model does deviate from the observed data to an extent. And we'll talk about potential sources of error here, right? So this has to do with certain flawed initial set conditions that I might have set up in tracker, right? It might not have been calibrated correctly. I might not have taken into account every possible thing that could have impacted the slinky, because the video isn't mine, right, of the slinky. I have no way of knowing what the exact conditions were on that day, so it could have been something like wind or extra drag that I didn't account for in our predicted model. And generally, of course, there's a human error element to tracker as well, right, because you're manually clicking on every frame. Finally, right, the discussion questions. What would happen if we added an object to the slinky? And this is the what if question here. Would it still stay in place? And the answer is yes. The motion would be completely unchanged, as if no additional object was added. Right? And that's because even if we add an additional mass, basically, the tension and the force acting downwards are still going to cancel out, and then the slinky is going to stay in, it's still going to stay in place, right? Basically, that's not going to change that, even if we add additional mass. And finally, the bottom of the slinky stays in place because of Newton's first law, right? Straightforward enough. The object at rest stays at rest unless acted upon by an unbalanced force. So thank you very much for watching this video. I hope this will help for you. Thank you.